right. We'll continue now a bit, same lines of thoughts, but now applied in some different use cases and also using some different tools. So what I'll be talking about in this session will be more PET imaging of neurotransmitter systems, and I'll be focusing on the pre-processing part, and then Granville Matheson will take over and focus on the quantification part in the second part of this. Right, I just need to remove this thing here. I have no disclosures. So the learning goals for today, or for this session at least, is that you should be able to understand the basic principles of brain molecular imaging, more directly PET. And then the second thing is learn how to access and pre-process brain molecular imaging data. And so this is hands-on, educational, and I prepared some code. It's a Jupyter, well, it's a GitHub repo where there's a Jupyter notebook. And what I'll do is that I'll first go through my set of slides, and then the goal is to dig into that notebook after. And again, it's tricky with pre-processing. You know, it takes time to run. I have 40 minutes. So let's see how far we get. I would also mention it's very different how people have Mac computers or Apple computers. They have a Linux system. They have Windows, other types. So we'll do it as good as we can. The main tools that I'll be talking about today is the robust head motion correction workflow called PET-Prep HMC. I'll talk about PET-Prep extract tags for doing co-registration, segmentation, and extraction of time activity curves. And then finally, I'll not dig that much into it, but this is also a PET surfer pipeline developed by FreeSurfer that has been converted into a NiPipe pipeline as an example. All right, so you've all seen this today. Maybe a few others have joined along the way, but just to go very briefly through the process is that PET brain receptor imaging 101, you start with a cyclotron that can generate some tracers. This is just an example of an 11 carbon. It could also be something else like fluor-18. You develop a tracer, you inject it into the body, into a cubital vein here, and then it goes to the brain where it accumulates. Then you can measure blood accordingly to get what we call an input function, often denoted as CP. Once we've corrected it for metabolites, you get this curve here. Then the PET data that comes out, it looks something like this. Often you want to do some sort of co-registration to an anatomical image. Then you get out these time activity curves at the regional level, but you can also get out these parametric images, in this case showing the total distribution volume, VT, as was mentioned in a previous talk. Okay, so my goal with this talk is to basically walk you through the different steps and why they're important. And the first thing that you often do to PET data, at least dynamic PET data, is that you do motion correction. And so the goal is here to make sure that as they're lying inside the scanner, sometimes they lie there for several hours, you want to make sure that their head has not moved over time. Because if one frame has moved this way, and you're comparing that over time, you're basically, you may end up in a region that has nothing to do with the region that you're interested in. So what you want to do is that you want to register all these frames to each other, thereby doing proper motion correction. And what I'm showing you here is just an example without motion and an example with motion, and I'll get back to that in a bit. The next important step that you then do after motion correction is often some sort of co-registration. And it's under the assumption that you have an anatomical corresponding image available. And as you can see here for PET, often we don't have the anatomical information available. Here you see just uptake in the putamen. You don't see the deep, or you don't see the cortical patterns here. So in order for us to dig down and look into specific regions, we need to register the PET to the MR. Often we would delineate regions on the MR and then apply that to the PET data to get these time activity curves. And then moving on to segmentations, often we do this directly on the MR data. And there's, of course, a lot of different choices that you can make. What I'm showing you here is an example of the AAL atlas that's available through SPM. It has this set of region definitions. I'm also showing you here on the right the FreeSurfer Desikan Kalyani atlas, which is slightly different, and also here applied to the subject space and not to an anatomical template space, which I would argue gives you better precision at the subject level. Then after segmenting the regions, depending on what atlas definition you have been using, then sometimes in the PET field, we also apply this extra step called partial volume correction. And the idea is really that because we have limited spatial resolution originating from our scanner, often the output looks something like this. And what you can see from this image is that it obviously does not respect the cortical boundaries, the gray matter in the cortex. You see that it has spread out into the white matter, but you can also see that it has spread out across cortical folding patterns. So the idea with partial volume correction is that you try to account for this spillover and spill-in effects. And there are different assumptions, there are different methods. Again, that's how it is in science. But the goal is to basically correct for this limited spatial resolution. So you get images at the end that looks something like this, where you can kind of like imagine that the signal has been pushed back into the gray matter. Then final step is that you extract time activity curves, and Graham will get back to that, how to model that after. But the goal is really that you have your atlas, you can extract your time activity curves, so the radioactivity in a given region over time. That is what you see here. All right. And you've already seen a few examples today, but I'll just we're gonna look at a few more examples just to get a sense of the quality and variability of this data, because it's quite important in terms of both methods development, but also in terms of understanding the data. So let me just show you the first data set here. So what you see here, you inject the tracer, it accumulates over time, it peaks at around here, and then it goes down again. So what you should take away from this is that, again, in the beginning when we inject the tracer, we basically have no signal in the brain. We don't have any signal. And then what you should also take away from this is that once we get to the end, depending on how long the subject is inside the scanner, you also lose a lot of information because the signal is decaying over time, you get washout of the brain. So you also lose some information here at the end, making this a very interesting problem, at least from a both motion correction perspective, but also from a registration perspective in general. All right. What you should also notice, and I'll get back to that, is that some PET images, they have these so-called striping patterns. You see that there's a lot of signal out here. That's because it's been reconstructed with a filtered back projection. And let me just show you how it could look in newer scanners. I have to continue. Where you've used a different type of reconstruction. And again, having this notion on how much can we compare data, these things matter, so please be aware of them when you go out and process your own data. All right. So this is example number 2. You also see no signal in the beginning. It accumulates over time, peaks at around here, where you get a very nice signal, and then going back to this decaying signal again, with the peak at around, where was it best? Before, something like this was probably the best. Okay, so what are the differences between these two data sets? I can tell you that both examples are using the tracer 11 carbon DASP, which is targeting the serotonin transporter. The differences are that these were acquired from 2 different scanners. First, the Siemens HR Plus scanner, that was example 1, whereas the the second one I showed you that looked like it had higher resolution, and that's correct. That was from the Siemens high resolution research tomograph. The resolution of the Siemens HR Plus, it's between 5 to 8 millimeters. And again, bear in mind that the cortical thickness is about 3 millimeters. So this matters a lot in terms of the partial volume effects that you will have present in your images. Whereas for the high resolution scanner, you're about 2 to 3 millimeters. And the example that Ariana showed this morning with the new NeuroExplorer high resolution scanner, you're down to 1 millimeter. So it depends a lot on what kind of signal at what given region you're interested in that you can capture based on this. What you can also see here is that the two scans, they used very different framing information, so that matters as well. The first scan, it was 120 minutes, whereas the other one was 90 minutes. And then what I just mentioned previously, the first one was a filtered back projection, and the second one was an iterative reconstruction algorithm using an ordered subset expectation maximization algorithm to reconstruct the data. And this is what you see in newer scanners, and usually they perform the best, but you should just be in mind that if you have data that uses filtered back projection, you will have these striping patterns, and they can be quite important when you apply either motion correction or some sort of registration, because it captures signal outside the brain, and that might disturb things. Okay, so based on this notion of the data quality, how can we come up with robust workflows that can be to use to process the data? And the first thing that we should be aware of is that we have differences in resolution between frames. So some frames, they have high signal-to-noise ratio, some frames, they don't. What can you do to that? Well, for example, you could choose to smooth the data to boost the signal-to-noise ratio. The second thing is that the first frames, they have very little spatial information. And so what you can do in terms, if you want to do motion correction, for example, is that you need to make some assumptions. And one thing that's commonly done is that you assume that motion to be similar for some of the first frames, which is often up to until 2 minutes. So you could see that after 2 minutes, you start to have signal in your brain. And then what you would do is that you would then say, okay, from those 2 minutes, I cannot say what happened before that, but I'm assuming that there was no motion within that 2-minute time frame. And then you can basically do motion with that 2-minute time frame and apply that to all the previous frames to also do motion correction on that. The second thing, or the third thing, sorry, that you can do is that you can remove signal or noise from outside of the brain. That can be done via some thresholding of individual frames. And then finally, it's the same in the fMRI literature and also other types of imaging data. What is a good reference frame? Is it the mean across frame? Is it a frame with high signal-to-noise ratio? And a mean frame is probably fine if you don't have any motion, but you can imagine that if you actually have frames with a lot of motion, you will get a smooth version of that that will tend to spread out signal. And so in terms of doing registration on that after might actually have an impact. So it's important to keep in mind. There's no consensus in the field how to do this, but I would, one of the tools that I'm showing in this session is actually frame independent. So it's doing frame by frame registration, so you don't have to select a reference frame, which is quite nice. So let's try to dig into it. The first tool that I want to mention or go through here is a robust head motion correction workflow called PetPrep HMC. And basically what it's doing is taking into account all these things that I just mentioned. So basically it's doing some smoothing before registration. It's also doing some individual thresholding at each frame. And then it's basically doing frame-to-frame alignment. So doing motion correction without choosing a reference frame. And you will try to run this in the Jupyter Notebook in not too long. But basically what you get out is these visualizations where you have, without motion, correction, and here with motion correction. You also get out these curves where you can see at what frames you had motion. And then it's up to you as a researcher to decide what should I do with this. Because often we can live with a little bit of motion, but as was just mentioned by Alexander Hammers, is that attenuation correction is important. So if you have a PET frame that is suddenly moved a lot, it will actually be impacted by the attenuation correction, and that might impact your signal. So again, it shows you these motion diagnostics, and then it's up to you to decide what to do with that and whether you can live with it. Right. The way that this can be executed is as a bits application. So you can either run it in Docker or you can run it as a Python script here, where you run this run.py file. The input is the bits directory to the raw data, output data. It's up for you to define. Often it goes inside the derivatives directory, inside the bits directory, and analysis level participant. And then you can choose a lot of different things as well. You can choose motion correction start time. So at what frame there's enough information for you to do the motion correction. The default is 120 seconds. You can also choose how much to smooth your images prior to doing motion correction. And you should bear in mind that the smoothing is only applied to determine the registration between frames. Once we've estimated those transforms, you apply that to the original data, so you get out the same resolution as you started with. And then finally, you can also use the thresholding, which is a percentage between 0 and 100%. And the default here is 20, which often gives you a good visualization of the brain, removing these striping patterns, as I mentioned before. Right. And you'll get to do this later on in the notebook, or at least see how it can be done. The next thing that I want to move on to is now that we've done the motion correction, now we're interested in extracting time activity curves, and that can be done using this tool, PetPrep Extract Tags, which is also a bits application to do. And basically what it's doing is that it's taking the anatomical data, it's registering the PET data to the MRI, it's doing segmentation for the MRI, mostly using, at least for now, region definitions defined by FreeSurfer, which are subject-specific segmentation. We're also working on including that you can basically come with whatever segmentation that you want, so it's up to you what you want to do. But in general, I would say that the signal is more stable if you stay in the subject space for regional analysis. And the reason why that is that you respect the cortical, like you respect the subject-specific anatomy. You don't go across boundaries, and that tends to have a better performance and better reproducibility. Then I'm just showing you an example here using Falipride, which is a dopamine D2, D3 tracer. And basically, we're extracting the time activity curves for these different regions. I'm just showing examples. This can be done for every tracer that you have in mind. All the output data is in the bits derivatives following the current PET specification. It's not finalized yet, but we're working on it, and I encourage everyone here to join those efforts. But the idea is really that we have now defined how should the raw imaging be done, and now we're trying to define also how should the derivatives be done. And why is this so neat? Well, it's quite neat because you now can start to develop software that expects a certain input structure. So you can create your own motion correction workflow, or you can create your own extraction workflow. But because you know that the data follows this format or this structure, it's basically a plug and play case. And what you will also see is that the outputs from this PetPrep extract tags, which are time activity curves, either at the regional level or in surface or volume space, is that they can then be applied to tools like KinFitter that Granville will focusing on, where you can now start to implement the different models, and that has already been done. But because the tools, they expect this certain structure, it's easy for them to just continue where others left off. So you don't need to be an expert in both motion correction and registration and so forth. You can rely on these structures. The way that it can be executed is also as a bits application. So following motion correction, you can again run it just as a Python script here, as a bits application, giving it your input and also the output here. And then it will run the workflow, and you will get the outputs that you expect. The outputs, or the main outputs, are these time activity curves, which are structured in a TSV file, where you have the first column that's defined as frame start, and the second column as frame end. And then you have all these different regions, and I'm here can be loaded into PMOD. That's an industry partner doing pharmacokinetic modeling. It can also be used for tools like KinFitter that Granville will go into. The reason why I'm mentioning this is that a lot of PET groups, they use PMOD for modeling. So this is kind of like my selling point, that we're, from the PET bits derivatives perspective, we're interested in not making it different, that these kind of tools can be used. So outputs, again, all these different region definition outputted into this TSV file, where we have the timing information here in the first two columns and the uptake for a given PET region over time for the subsequent columns. Then what is really nice about some of these tools is that we can start to leverage some of the great work that is being done by the FreeSurfer group, and that is, for example, sub-segmentation workflows. So what I'm showing you here is work done by the FreeSurfer group to do thalamic nuclei segmentation, where you get out these more specific region definitions. And because we can then use those as a part of our workflow as well, you can also get out time activity curve for these regions as well. And it's not just for the thalamus. These are continuously being developed. So this is also hippocampal subfield segmentation, where you have the different parts of the hippocampus. You can extract time activity curves from that. You can always discuss the use of partial volume correction in this, and you should be mindful about that as you go down in region size, you will have more partial volume effects, and you will also have more noise because you have smaller regions. Nevertheless, this can still be done, and again, it's up to you as researchers to decide whether it makes sense. Currently, we also have a few other segmentation pipelines included in this workflow. So we have a RAFE segmentation as well, and more segmentation are continuously being added to this workflow. Again, added in subject space. What it's also doing is that it's doing some co-registration diagnostics. So it's spitting out visualizations like this, where you have the PET and the T1 weighted data on top of each other. So you can basically verify that you did a good job in terms of the co-registration. Very important, because if you haven't done a good job on that, you will have some subsequent problems when you try to extract time activity curves. Let me just continue, if it allows me to do. What is also really nice is that now that we start to define these derivatives, we can also start to add that data back to, for example, OpenNeuro, or where we got it from. So this example with the COX-2, this data set is already available on OpenNeuro. We've started now already to add these derivatives back onto OpenNeuro. And that means that if you don't care too much about all those steps of both motion correction and pre-processing, well, you still have to do some other steps as well. You can basically go from here. You can go in and you can get just your time activity curves. You can get it from different regions. And again, then it means that we've basically been doing all the work for you, and it makes it more easy for others to come in and make good uses of this data without necessarily having the expertise to process the data, which I think is really useful. Right, and then I think we should try to move on to the demo. And let's see, we have some time, about 20 minutes, and again, you know, to those of you who are used to doing pre-processing of your data, you know that you cannot do these kind of things in 20 minutes. So my goal with this is more to expose you to how it can be done. And then depending on whether you want to run it locally, in my example case here, I'm actually planning to run it in Google Colab, because then you can actually install packages like FreeSurfer and FSL. You can install that inside Google Colab. Then the problem is that it's super fast to download because it uses Google Download. It's also very nice to install. When you want to run the workflows, that's when you run into problems, because of course there's some memory constraints. So some of these workflows will take a fair amount of time, but it's more to expose you to how it can be done, and then it's up to you to go ahead and do it. All right. So if you click on the link, and I can just, you will get into this GitHub repo that has a description here, and the main file that you're interested in using is this PET preproc tutorial collab. And my aim right now is to go down there and try to open this in Colab, but it is basically a Jupyter notebook. So if you already maybe have FreeSurfer installed, or if you have FSL installed, you don't need to do this. But all these things can be run in Google Colab or other places that allows for Jupyter notebooks. So let me just go through it here, just on the on the surface, and then the plan is for you to actually spend some time on going through this. So again, what I'm doing here is that I first collect the repository, so the GitHub repo, cloning this outreach repo, and then the next thing I'm doing is that I'm installing FreeSurfer. That can be done with this here. So it's if you run this in Google Colab, it will basically install FreeSurfer inside that, so you can use it. The next thing that you can do is that you can install the PetPrep robust head motion correction workflow, PetPrep HMC, and also just done by cloning the repo on GitHub and then installing it with pip install -e and then dot. That will install the motion correction workflow. Then there's also a download section inside the notebook. So here I've made a condensed version of this data set on the COX-2 that's available on OpenNeuro. There's just one subject in there with one session where you have all the raw data, including both the PET, MRI, blood data, but it also has all the derivatives, so all the outputs for these workflows. So you can either try to run the workflows yourself, or you can also already now start to inspect some of the outputs of this data. So basically what I'm doing here in this piece of code is that I'm basically downloading this condensed version of the data, which is currently located in a Dropbox, and then packaging out the data. You see that it has the subject-specific data, it has all this derivatives data, where it's been run using FreeSurfer. So that's the first main output of the derivatives. I've also run SMRI prep on this data, which is equivalent of fMRI prep, but on structural data, giving you all the outputs of that. If you scroll down further, just see if I can do it here. It's easier. You go through all the FreeSurfer SMRI prep. You get further down. And apparently it's not evident from here. But there's also all the outputs from the PET prep, both the head motion correction workflow and the time extraction, extraction of time activity curves workflow. Then to run the motion correction workflow, you both need FSL and FreeSurfer, so these need to be installed as well. You can also do this inside the Google Colab or do it locally on a server that you have access to, but you need these two packages to be installed. That can be done inside the notebook. It's giving you all these outputs. And again, just to be open, I don't expect you to finish this during this short amount of time, but this is just to show you how it can be done. Right. And then basically you go down here to this code here, and you go into your directory where you have the PET prep HMC workflow installed, and then you run this line of code on your data, and then it will run the PET prep head motion correction workflow as a NiPipe workflow. And I'm just showing you here how it will start to look, and then it needs to finish before you get all the outputs. But again, I provided you with the outputs, so you can either start to do this, or you can already now start to inspect some of the outputs. The same goes for the PET prep extraction of time activity curves, is that you can also just install that workflow by cloning it again from GitHub, installing it, and then running the workflow. So with that, I encourage you to check it out and spend, I don't know how much time I have, 10 minutes? 10 minutes? On at least, getting a little bit more familiar how these things can be executed. And then feel free to ask questions along the way. We'll try to make it a dynamic session, but the goal is for you to, sit on your own and try to go through this. And I'll go back to the link here. And again, I'll be standing here, so if you have any questions, feel free to come up, and I'll try to answer it along the way.
Martin, I have actually some questions on your presentation. So I have two questions. The first question about motion correction. So you said that you correct for the motion in the resulting PET images, but you don't go back to the raw data to correct also, say, the wrong attenuation correction. So do you have is there any way to do this? And how do you define too much motion to say, I need to discard this frame, and what do you do in that case?
Yeah, that's a great question. It depends on who you ask. So I've been, the way that I got my training was that, 3 to 5 millimeters is kind of like the max. If you see more motion than that, you actually have to go back and try to do a new reconstruction where you try to align the attenuation map. When it comes to reality, you will see that in the real world, you will see much more motion. And as mentioned previously, this is expensive data, and we try to do as good as we can, but this is definitely an overlooked aspect in the PET field. And this is often not really reported that much. So that's why at least we encourage with these kind of tools to be open about it. It is what it is, but it might impact subsequent results.
And second question, so you mentioned there is now atlases available that go a bit more deeper into substructures, but when is it okay to use them or not in comparison to the spatial resolution that you have? Is there any rules of thumbs that tells you can use this atlas or not? Both in terms of spatial resolution and also of signal intensity, right? Because if you have a high signal intensity, you see things a bit better than if you have a low uptake.
Yeah, that's also a great question. I'm not sure I can give recommendations on that. I mean, ideally you shouldn't go lower than the resolution that you have. If you look at the Nyquist theorem, also, I would not go down to lower than the resolution of the PET scanner, which definitely then speaks against using these subsegmentations. But the goal with using the subsegmentations is more that you want to make sure that you're not contaminating signal of a larger brain region. So I can give you an example of the thalamus and also the serotonin transporter here. If I can go back here. If you go and look at the serotonin transporter, it has a lot of signal here in this part of the thalamus, which is also a more of a gray matter part of thalamus compared to the bigger chunk here of the white matter. And if you include, just the entire thalamus, you will have some regions that, where it's higher, it'll be higher here, and it'll be lower here. And the question is just, is that a fair comparison? So in terms of getting more specific signal, you are interested in, hitting the spot without just, potentially contaminating it by other signal. So I think, that's my short answer. It's a long answer in general.
I also have a follow-up question that just came to my mind. So you showed ROI-based results. So now if they work on the tutorial, they will get extract time curves from regions of interest. Like Xin showed some voxel level results, right? So can we get at the voxel level with these kind of tracers? Is there any technical reason why we cannot, or anything we can do to actually make it possible?
Nope. You can also go to the voxel level. Again, quantification will be more noisy at the voxel level. So that's often why you apply some smoothing. And that has some trade-offs as well. It affects the spatial autocorrelation function. So it matters in terms of false positives. So again, Granville is probably the better one to ask, but maybe you want to add something. But it can certainly be done. And also in the prep extract tags, there's both a volumetric workflow and a surface-based workflow. So you can get out voxel-wise time activity curves and surface-based time activity curves as well, including options for doing the level of smoothing that you want to do.
I have a question. A question that I have is why to smooth the data after to perform partial volume correction, PVC? So
I should not do that.
Yeah, but not you, I think. But following the presentation, you said you was saying, okay, now there is a smoothing of the data. And the second slide, slide was PVC, partial volume correction. But from my point of view, of course, it's a contradiction, even if not you, but even if it's present in the PET results. And even if PVC in true is up in this moment, there is just only Richard Carlson suggested a way to correct PVC with a time activity curves, but normally it's performed just only with static images. I know if you have any suggestion, just to split this,
Yeah.
we spoke more times about smoothing this, not smoothing too small.
Yeah, I mean, in this workflow, in the main pre-processing steps I mentioned, I did not mention smoothing as a, usually it is the 5-step pipeline of motion correction, registration, segmentation, maybe partial volume correction, mostly not applied, and then, quantification or extraction of time activity curves.
If I may add something, so the reason, for the sake of the audience, partial volume effect correction is a means by which to reduce bias in the data, but while introducing variance. So if you have a young set of subjects and you have a diagnostic group, for instance, where you don't expect any volumetric differences, partial volume effect correction could well make your data worse. It's a necessary evil when we have diagnostic groups where we have, for instance, cortical degradation or we have different region sizes. So basically, it ought to improve our data, but these algorithms are not exact. They don't perfectly solve things. So I think, just for everyone's understanding, partial volume effect correction is something that we do when we need to, but if we can avoid it, it's until we have better algorithms, we tend to avoid it.
And then maybe one final addition to that is that if you ask the free surfer group, they would argue that you do partial volume correction like this, it gives you a better cortical representation, and then basically you project this data onto the surface, and then you do the smoothing along the surface, And that has been shown to have better bias variance properties than doing it in the volume space. And with that, you have 5 minutes left to explore the notebook. 3 minutes. Yeah. And yeah, any questions, feel free to come up and ask.
Hello, thank you very much. One question, so the motion correction only addresses between frame motion, which is technically like non-existent because it's the time frame between, it's continuous, right? So is there something to address intra-frame motion? Because there's probably slow drift towards one side that affects the whole frame and smoothes this a bit, first question. And second question, if we look at the small RIs, would you still recommend smoothing or partial volume corrections?
So the first one, you're absolutely right, that it is like the frames are like, it's a continuum over that frame, and you could have intra-frame motion, and that kind of like gets averaged out. So if you would ask some PET researchers, they would say that you cannot even do this kind of like post motion correction. You have to do it while you do the scanning, and then actually put it into the reconstruction to account for it there. But yeah, it's a trade-off. So that's a very good point. On the second one, it's difficult to say. It depends on the scanner as well, the resolution, but in general, what you will see, again, smaller regions, they're more noisy. If you have noisy regions and try to do partial volume correction, those regions will become even more noisy, and that means that it will be very difficult to do subsequent kinetic modeling or quantification on this. So I think, you will run into problems if you do this. And yeah, I think that's also why most people, they maybe stay a bit away from partial volume correction. But yeah, as Granville is mentioning, sometimes you have cortical atrophy, so you know there are differences, and then you need to try to take it into account.
Okay, thank you.
Thank you for the questions.
Martin, well, one last question.
Yeah, come, bring it.
On the topic of quality control, quality check, is there anything implemented in OpenNeuro, kind of automatic quality check of the data, or maybe just in terms of completeness, or like how much do we need to do if we get data from OpenNeuro, so BITS compliant and everything?
Well, so you know that when you upload data to OpenNeuro, it's BITS compliant. So it's basically validated using the BITS validator. So you know that it conforms to the BITS specification. So that just means that you have inserted information on, for example, injected radioactivity. You have the correct number of frames. You know that the data exists there. On the quality side, currently nothing is added, and that's where there are some tools with, at least on the MRI side, called MRI QC, and I know there are efforts to do that on all data on OpenNeuro. We're planning on doing something similar for the PET side. So if you would upload your data to OpenNeuro, we would run these diagnostics on it and basically put it back to OpenNeuro, so others can look into the quality of the data. Yeah. All right. Yeah.
Hi. Thanks. Actually, on this slide exactly, so I think this is really great that we have a co-registration diagnostics within the toolbox. If I know the question I have is there a way to specify the cost function that you're using to co-register
To assessing the cost function?
Yeah, so basically if there's an issue with the co-registration, are we able to change it so we have a better realignment?
Yeah, you can change the cost function.
Okay.
Yeah, so it's basically what's running under the hood here is the free server function called MRI correg, which is basically similar to the SPM implementation by John Ashburner many years ago. And you can choose different cost functions. Here it's using normalized correlation, which seems to perform quite well for these cases, but of course it can be different depending on your registration problem. It also allows you to do boundary-based registration, also from FreeSurfer. I would say, however, for PET, it's not generally something that I would recommend, because for PET, you don't always have the nice cortical folding patterns. So actually, a boundary-based registration would not necessarily work well.
Yeah, I mean, we'll depend on your trees we use.
Yeah, but great question. Thank you. All right. Well, with that, I hope you at least had time to look at the notebook. At least now you know where it is, so you can go home and use it and try to run it on this data. And with that said, I want to move ahead and introduce the next speaker.